Okay, so we've got, obviously, there's a gas law problems. So when you see a gas law problem, what's like one of the first things you want to knock out right away?
Atmosphere conversion.
You could do conversions into atmospheres, but it's probably actually not necessary. I would switch the temps to Kelvin. Under no circumstances will any of the problems allow you to be, will they be correct if you do them in any temperature other than Kelvin. So if you see temperature, it doesn't really matter what problem you're doing, just convert it to Kelvin and work from there. So I'm gonna need 273 here, so 323. And then 273, so 5, 8, 285K. Okay. What are we looking for in this problem? I'm sorry, what? Yeah, we're looking for a volume in this case, right? So I'm looking for this volume, and the only unit that has volume in it is this little milliliter right here. So I'm going to go ahead and start with that. So I'll put 300 milliliters in the numerator right there, and that'll give me a volume unit. Okay, so now we have to think about what happens to this, and then what those changes would do to the volume. So what happens to the temperature? It increases. So if you heated something up, a balloon per se, and what would happen? Tell me what would happen to its volume. It would get bigger. All right, so hotter air, bigger balloon. So I'm going to put 323K in the numerator and 285K in the denominator, and both of those will cancel out. All right, and we also had a change in pressure, and in this case the pressure went from 750 to 360, so it was reduced. So if you reduced the pressure on a balloon, what would happen to the size of the balloon? It would get bigger, right? I'm squeezing it, and now I'm not squeezing it as hard, so the balloon is allowed to expand. So this would be, I need to put these in a way that will give me a bigger number. So I'll put my 750 millimeters of mercury in the numerator and 360 millimeters of mercury in the denominator. And both of these ratios of temperatures are going to give me a larger volume. So what do we got here? Oops. $300 times 708 is what I got milliliters. Okay. What kind of gas, which gas law was that? Combined, yep. So I got the pressure of a gas is reduced from that pressure to that pressure as the volume of the container is increased from that size to that size. What would be the final temp? All right, so I see a temperature here, so 273, 383 Kelvin, so I got that knocked out. I'm looking for a temperature, so I'm just going to go ahead and start with 383K. And the gas pressure is reduced. Okay, so if I reduced the gas pressure, for the gas pressure to be reduced, what would have to have happened to the temperature?
Down.
It would go down. The only way this thing's pressure would go down is if the molecules got cooler. So I'm going to put the 1,000 millimeters in the numerator, or denominator, sorry, and 750 in the numerator. That way I get a smaller temperature. And the container's volume is increased by moving a piston from 75. All right, so how would you get a container to go up? To be bigger, what would you have to do to the temperature? I'd have to increase it, right? So this time I'm going to have to write this in a way that would increase the K. So I'll put 320 milliliters here and 75 milliliters here. So these two parameters, the volume and the pressure, are fighting each other in this problem. And then we'll see who wins and if the temp goes up or down. So I've got 383 times 750 times 320 divided by 1,000 divided by 75. I got 12, 3 sig figs, 3, 0. And then what would you want to do next? You want to change it back into Celsius. So if I minus 273, I can turn this into 953 degrees Celsius.
Do you want to wait to convert the significant figures until you get to the last?
You do. I just looked at it and it turned out to be okay. So this would have been 225. Okay, next one. We're gonna do a single replacement reaction. And it's zinc and HCl. So zinc and HCl, solid, aqueous. And what am I gonna get on the other side?
Hydrogen gas, zinc chloride.
Okay, so we get hydrogen gas and zinc chloride. What type of chemical reaction is this? Single replacement, yep. Something by itself, and then it's not by itself, and something else is by itself. Why is the formula ZnCl2? Because the zinc always has a charge of +2 when it's in a it's also a redox reaction for sure. So zinc's always got a +2 charge, so I'm gonna have to cancel that out. So we need to put something up here, which is what? I need to throw a 2 in front of the hydrochloric acid. Okay. So if I start with 43 and 75 of the zinc and the HCl, what's going to be in the container when I'm done? All right, so I'll just start off with 43 grams of zinc. Um, 65.39, and then zinc and zinc. And it doesn't really matter which one I go to. I'll go to the hydrogen gas. So I don't know where I wrote zinc there. H2. And I need to put the coefficients in. So I have a 2 for the, sorry, I have a 1 for each. And then for every 1 mole of the hydrogen gas, it's 2.0159 for the mass. And I end up with 43 times 2.0159 divided by 65.39. I get 1.3 grams of hydrogen gas. All right, so now let's use the other 75 grams of HCl. HCl, 1 mole, and then HCl. And that's 35.45, no, 453.00795. So my mass for my HCl is 36.5325, and then HCl, and then H2, and then need a 1 here, and a 2 here, and a 1, H2, 2.0159, H2, H2. And so I've got 75 divided by my mass, divided by 2, but times 2.0159, so 0.51 grams. All right, so can you... You got 2.11? Let's see if I punch this in here. Times divided by... Oh yeah, I hit divide instead of times. Yeah, 2.1. That's better. 2.1. Great. Okay, so 2.1 for my mass. So what do I know now? The limiting reactant is zinc. The moment I've made 1.3 grams of zinc, what happens? The reaction stops because there's no more zinc. So what do you know is left in the container? HCl, and then also the hydrogen gas and the zinc chloride that I've made. So this is how much hydrogen gas is in the container for sure. We already calculated that. So what I need to do is calculate how much zinc chloride is in the container. So let's do 43 grams of zinc, 1 mole of zinc, 65.39 grams of zinc, 1 mole of ZnCl2, 1 mole of zinc, 1 mole of zinc chloride, zinc chloride, zinc chloride. I got 35 point. How am I forgetting this? 453 times 2 plus 65.39 equals, I got 100.843 times 43 divided by 65.39, and I got 66 grams of zinc. Okay. One more thing to do. And what's the last thing I need to do? I need to figure out how much HCl is left. So I've got 43 and 75. Is it weird? So 118 grams of reactants are in the container. So when I'm finished, I have to have 118 grams of product plus leftover reactant. So what I've got here is 66 plus 1.3. So I've got 67.3 grams of product. So if I say I got 118 grams and 67.3 grams, then whatever's left over is my mass of leftover HCl. So I got 118 minus 67.3. Yeah.
For the third one?
Yeah.
I mean, you still do it the same way, but I think maybe I got 89 grams because I got for zinc chloride like 134 or something. 136, yeah.
Oh,
The grams.
there's the multiplication sign did not go in there again. Dang it. Yeah, 136. Grr. So this is 136.296 times 43 divided by 65.39. 80. Looks like 90. All right, so let's get rid of this. So then I get 91.3, 91.3. So 118 minus 91.3, and I get 26.7 grams of HCl that's left over. Okay. Thanks for catching that twice. So how many moles? So when you look at this problem here, these are obviously gas law problems, so we can do the 273. So I get 298 here. Great. Looking at this problem, this one looks different than the other gas law problems. What's different about it? What?
For moles.
We're looking for moles this time. We hadn't seen that, but really the important thing to notice is there isn't any before and after. There's no P1, P2, or N1, N2, or V2, V1, none of that stuff. So this must be an ideal gas law problem because it's just got the actual each of them. So there aren't any moles up here. So what I'm gonna need to do is use the ideal gas law constant to get me moles. So then I'm gonna put 0.08206 liter atmospheres, moles, Kelvin, into my calculation like this. So why did I put the number in the denominator?
So the moles would be times, we can end it with moles.
I'm looking for moles and I want the mole unit to be in the numerator, so it's in the numerator. And so now I just need to cancel everything else out. So we already did a calculation for temperature, so I'll put 298 K here and cancel out the K. I've got an atmosphere number, so I'll put 2.5 atmospheres here and cancel out the atmosphere. I can take this thing right here and just turn that into 0.1 liters if I move the decimal place over 3 spots. So I'll put 0.1 liters here, and then the liter unit cancels out. And see what we get. There you go. That's how many moles of gas I got. At standard temperature and pressure, 3 liters of gas is known to have a mass of calculated its molar mass. Okay, so what do you need for a molar mass? What are the units for molar mass?
Grams per mole.
Grams per mole. So I have a grams unit right there, and I could use the ideal gas law to give me a mole unit. So I'm going to start off by putting 9.5 grams here, and then I'll put grams per mole. Okay, so 0.08206 liters times atmospheres divided by moles and Kelvin. I have the 2 units I'm looking for where they're supposed to be, moles in the denominator and grams in the numerator. So now I just need to get rid of the liters and the temperature and the atmosphere. So the nice thing about that is at STP, it's 1 atmosphere of pressure. So the ATMs cancel. And at STP, it's 273 K because it's 0 Celsius. So that cancels out. And then I just need to get rid of the liters, and that was given as 3. So 9.5 times 0.08206 times 273 divided by 3. Divided by 3. Huh. Why does that not look right? Liter unit cancels. The atmospheres cancel. 0.08206 liter atmospheres moles Kelvin. 273 and ATM. 9.5 times 0.08206 times 273 divided by 3. Ah, that's better. 70.9 grams per mole. Do we have questions about this one? What's wrong?
How come on the ideal gas law, I see that it's standard pressure, but how come you have to convert it into like ATM and like all of them Kelvin, whereas in the other laws you don't have to? Is it because it's not standard?
Nope.
No?
What are the units on R?
Liters, atmospheres, or more, okay?
That's why.
Okay.
In every ideal gas law problem, you will have those units from the R. So how do I cancel them out? I have to have them in those units. If they're not in those units right there, then I can't actually multiply the things together, or I'll end up with units that don't cancel. So this, what was the questions about the second one on this page?
like, how'd you get, again, how'd you get, like, how did you determine that the atmosphere is on the bottom? Molar mass.
I'm trying to calculate a molar mass, right? And Steve told us right at the beginning that the molar masses units are grams per mole. I didn't use, obviously, the ideal gas law equation per se. I mean, we actually did, it just doesn't look like it. So all I'm trying to do is create a number whose units are grams in the numerator and moles in the denominator. And then I just throw everything into the railroad track to give me grams in the numerator, moles in the denominator, and everything else cancels out.
So,
It's all units. That's all there are with nursing. No equations. If I were to tell you that this was an element, could you tell me which element it is? It's a trick question. This would be a terrible question to give you on an exam, but it's funny right now because it doesn't matter. I mean, there's some tricks you should probably be able to figure out from this, but say again? It's chlorine, right? Chlorine's mass is 35.5, almost. So how is this guy's molar mass 70? It's a chlorine, it's a diatomic. It comes as a Cl2. Plus, we're talking about gas laws, right? So when you're talking about gas laws, your eye, if you get a question like that, your eye should immediately be drawn to all the green things on the periodic table because they're all gases. And none of them have a mass anywhere near 70.9. But if you double one of them, chlorine nails 70.9 right on the number. Okay. All right, so I got a container, and inside the container, the xenon gas is traveling at 150 miles an hour. And there's also some helium gas in the same container. How much faster is the helium gas moving? First off, how do I know the helium gas is moving faster? It's in the same container. It's smaller and they're at the same temperature. So if they're at the same temp, they have the same kinetic energy. And if a xenon is much heavier than a helium, then the helium must be traveling a lot faster. Okay, so I'm gonna say rate of one gas, I'll say rate of the helium divided by rate of the xenon. And that's equal to the, well, we know the rate of the, doesn't really matter, let's just write rate xenon down here. The molar mass of the helium is 4.00260, and the rate, or the mass of the xenon is 131.29. All right, so let's do this. That's totally backwards. 131.29 divided by 4.0026. Okay, so 131.29 divided by 4.0026. So I get 32. 33. So this is 33 over 1. That's the rate difference. So the helium is moving 33 times faster than the xenon is. So how fast is the helium moving? Whatever the xenon's speed is times 33. So 150 miles per hour times 33. So 150. So I get 4950 miles per hour.
Do you have to take the square root of 33?
Yep. Yep. You gotta take the square root. Yeah. Yep. Clear. Square root 33. Close equals. That's better. It seems like a more reasonable. Looks like that'll go to 8. 770 miles per hour. Okay.